K2-18b. The mystery of life on planet Ocean, the exploration of the universe, is an exercise in profound humility, a realization that we are but a mote of dust suspended in a sunbeam, a tiny fragment of a much larger and more ancient narrative that we have only recently begun to decipher through the lens of modern science. As we cast our gaze toward the constellation Leo, approximately 124 light-years from our own solar neighborhood, we find an enigmatic world known as K2-18b, a planet that fundamentally challenges our terrestrial-centric definition of habitability and existence. Carl Sagan often reminded us that the surface of the Earth is merely the shore of the cosmic ocean, and it is only in the last several decades that we have begun to wade ankle-deep into its vast and uncharted depths, searching for answers to the most fundamental question of our species: are we alone? The search for life on a world like K2-18b is not merely a technical search for oxygen or liquid water. It is a profound search for the very atoms that go into a living thing and a quest to understand the unique, complex ways those atoms are put together across the vastness of space. Neil deGrasse Tyson provides a sobering and essential analogy for our current state of exploration, arguing that claiming there is no other life in the universe based on our current, limited data is akin to scooping up a single cup of water from the sea, looking at it, and claiming that because there are no whales in that cup, there must be no whales in the entire ocean. This realization demands that we acknowledge the sheer scale of our ignorance, recognizing that the few thousand exoplanets we have discovered represent a statistically insignificant sample of the hundreds of billions of stars in our galaxy alone. We stand today at a significant crossroads of cosmic discovery, where the James Webb Space Telescope has detected chemical fingerprints that could either represent the first definitive signs of alien life or the signatures of an exotic, abiotic chemistry that we have yet to fully comprehend within our current models of planetary formation. K2-18b has emerged as the archetype of a newly theorized class of exoplanets known as Hycean worlds, planets characterized by hydrogen-rich atmospheres and global liquid oceans, and it may represent our best opportunity to determine if we have finally found another cup of water that might actually contain a whale. This investigation into K2-18b is more than a study of a single exoplanet. It is an interrogation of the laws of physics and chemistry that govern the potential for life across the Milky Way, forcing us to rethink the boundaries of the habitable zone and the chemical precursors required for biological evolution. By exploring the specific environment of this sub-Neptune, we are attempting to bridge the gap between the familiar rocky worlds of our inner solar system and the icy giants that reside in its outer reaches, effectively reconstructing the history of how water and volatiles are distributed throughout the cosmos. Our journey toward K2-18b is a testament to human curiosity, a drive that compelled us to leave the savannas of Africa and now compels us to bridge the light years between stars in search of a mirror that might show us ourselves. The potential habitability of K2-18b is inextricably linked to the nature and behavior of its host star, K2-18, a red dwarf located roughly 124 light-years from Earth in the constellation Leo. M-type dwarf stars represent the most common stellar population in the Milky Way galaxy, comprising nearly 3/4 of all stars, yet they present a profound paradox for the emergence of life. While their extreme longevity, often lasting for trillions of years, provides a remarkably stable window for biological evolution to occur, their early lives are frequently characterized by intense magnetic activity, high-energy flares, and volatile outbursts that can strip the atmospheres of nearby planets. K2-18 itself is categorized as a spectral type M2.5v star, which is significantly smaller and cooler than our Sun, possessing only about half of the solar mass and approximately 2.3% of the Sun's total luminosity. When we examine the specific stellar properties of K2-18 compared to our own Sun, the differences are stark and defining for the system's architecture. While the Sun is a G2V yellow dwarf with an effective temperature of 5,778 Kelvin, K2-18 is a cooler M2.5v red dwarf with a surface temperature of only 3,457 Kelvin. This greatly reduced energy output dictates that the habitable zone is situated much closer to the star than in our own solar system, with K2-18b completing a full orbit every 33 days at a distance of approximately 21.4 million kilometers. or 0.14 astronomical units, placing it squarely within the conservative boundaries of this habitable region. Despite its small stature, K2-18 is a sentinel that subjects its planets to radiation environments that are entirely alien to the conditions found on Earth. High-energy X-ray and ultraviolet fluxes from K2-18 are significantly more intense than those received by Earth from the Sun, acting as a double-edged sword for any potential biosphere. While such radiation can provide the necessary energy for prebiotic chemistry, it also relentlessly drives atmospheric escape through photoevaporation, a process where high-energy photons heat the upper atmosphere to temperatures exceeding 10,000 Kelvin, inducing a hydrodynamic outflow. Observations suggest that K2-18b may possess an extended hydrogen-rich exosphere formed as intense ultraviolet radiation photodissociates water molecules, causing the lighter hydrogen to bleed into the void of space. Furthermore, the presence of a second, inner planet, K2-18c, adds gravitational complexity. K2-18c is a warm super-Earth with about 5.62 Earth masses, orbiting the star every 9 days on a non-coplanar orbit, potentially influencing the tidal heating and orbital stability of K2-18b. Recent studies utilizing X-ray observations from missions like XM, M-Newton, and Chandra suggest that while K2-18 is a faint X-ray source with an activity level of approximately 10 to the power of -5, it still exhibits small flares that contribute to the cumulative radiation dose received by the planet. This delicate balance between stellar aggression and planetary resilience is the defining characteristic of the M-dwarf systems that dominate our galaxy. One of the most significant and persistent mysteries in modern exoplanetology is the existence of the Radius Valley, also known as the Fulton Gap, which describes a statistical scarcity of planets with radii between 1.5 and 2.0 Earth radii. K2-18b, with its radius of approximately 2.61 Earth radii and a mass roughly 8.63 times that of our home world, sits on the far side of this valley, categorizing it as a sub-Neptune. These worlds are entirely absent from our own solar system, creating a fundamental gap in our understanding of how planetary formation and evolution work across different mass regimes. The calculated density of K2-18b, estimated at approximately 2.67 grams per cubic centimeter, is intermediate between the rocky, high density of Earth and the gas-rich, low density of Neptune. This specific density profile strongly implies that the planet is not a solid sphere of rock, but is likely composed of a significant water-rich or volatile-rich interior enveloped in a thick, hydrogen-helium-dominated atmosphere. This bridge status makes K2-18b a primary laboratory for testing our most advanced planetary models, as researchers debate whether it is a mini-Neptune with a crushing gas envelope or a Hycean world with a condemned liquid surface. The transition between these two distinct states is governed by the total mass of the hydrogen envelope, which in the case of K2-18b is estimated to be no more than 6.2% of the planet's total mass. This relative thinness is the absolute key to its potential habitability. If the hydrogen layer were much thicker, the atmospheric pressures at the bottom would be too high for liquid water to exist, forcing the water into exotic phases of high-pressure ice, even at relatively high temperatures. The cause of the Radius Valley itself is often attributed to two competing mechanisms: photoevaporation and core-powered mass loss. In the photoevaporation scenario, high-energy X-ray and ultraviolet radiation strip the gaseous envelopes from planets that are too small or too close to the star, leaving behind bare, rocky cores. In the core-powered mass loss model, the thermal energy released by the cooling planetary core itself is sufficient to blow away the atmosphere over much longer timescales, roughly 0.5 to 2 billion years. K2-18b serves as a vital data point in this debate, as its location near the edge of the valley allows researchers to study the boundary conditions of atmospheric retention and determine which of these evolutionary paths is most common in the universe. By determining the exact composition of K2-18b, we can begin to understand if sub-Neptunes are primarily water-rich worlds or simply failed gas giants. The Hycean world hypothesis, originally proposed by Nick Madhusudhan and his team at the University of Cambridge in 2021, represents a true paradigm shift in the search for extraterrestrial life. Traditionally, The field of astrobiology has focused almost exclusively on Earth-like planets, rocky worlds with nitrogen-oxygen atmospheres and surface liquid water. Hycean worlds, however, expand the definition of the habitable zone significantly. Because molecular hydrogen is an exceptionally potent greenhouse gas, a Hycean world can maintain liquid water at much greater distances from its host star than an Earth-like planet ever could, provided the atmosphere is not so thick as to induce a runaway greenhouse effect. Furthermore, these worlds can be much larger and more massive than Earth, reaching up to 2.6 times its radius and 10 times its mass, making them far easier to detect and study with current instrumentation. The fundamental structure of a Hycean world is defined by a hydrogen-rich atmosphere overlying a global liquid water ocean, a configuration that is particularly conducive to astronomical observation. Hydrogen atmospheres are naturally extended, puffing up much further into space than the heavy, compact atmospheres of Earth or Mars, which allows more starlight to filter through during a transit. This leaves behind distinct spectral fingerprints that telescopes like the James Webb Space Telescope can detect with unprecedented clarity. In this context, K2-18b serves as the primary prototype for this entire class of planets. The hypothesis suggests that life on such worlds would be entirely aquatic, thriving in oceans that could potentially harbor more metabolic energy than Earth's oceans due to the reductive nature of the hydrogen-rich environment and the abundance of available chemical gradients. However, the habitability of Hycean worlds is not without its limits. Factors such as orbital eccentricity and the specific albedo of the planet play critical roles in determining surface temperatures. For K2-18b, a high albedo, perhaps greater than 0.5, is likely required to keep the surface cool enough for liquid water, given its proximity to its star. Some researchers have even proposed the existence of dark Hycean worlds, where the planet is tidally locked and life exists only on the permanent night side, or rogue Hycean planets that drift through the void without a host star. This diversity of possible environments suggests that the Milky Way may be teeming with habitable real estate that looks nothing like our own planet. The arrival of the James Webb Space Telescope and its Cycle 1 observations of K2-18b transformed the search for life from theoretical modeling to empirical analysis. Using the near-infrared spectrograph and near-infrared imager and slitless spectrograph instruments, researchers captured the transmission spectrum of the planet as it passed in front of K2-18, revealing the definitive signatures of methane and carbon dioxide with high statistical confidence. In a hydrogen-rich atmosphere, the presence of these specific carbon-bearing molecules is highly significant for our understanding of the planet's surface conditions. If the planet were a typical mini-Neptune with no surface ocean, chemical models predict that ammonia should be the dominant nitrogen-bearing gas in the atmosphere. However, the James Webb Space Telescope data revealed a surprising and statistically significant ammonia deficiency, with the gas being nearly absent from the observable layers. Ammonia is highly soluble in water, and its nearly total absence, below 100 parts per million, suggests it has been scrubbed out and dissolved into a massive, global liquid ocean, providing the first strong empirical evidence that K2-18b is not just a ball of gas. The specific molecular detections within the atmosphere of K2-18b provide a nuanced portrait of its potential nature. Methane has been confirmed at high concentrations, a finding that supports the hydrogen-rich atmosphere and hints at a possible biogenic flux, while the presence of carbon dioxide indicates a carbon-rich environment that aligns with the Hycean model. Furthermore, the ratio of methane to carbon dioxide detected suggests a temperate climate, reinforcing the idea that the planet resides in the habitable zone by its internal thermochemistry. While earlier observations from the Hubble Space Telescope were originally interpreted as water vapor, the higher resolution of the James Webb Space Telescope has clarified that the primary features in the spectrum are indeed these carbon-bearing species. Despite these findings, the scientific community remains divided. Some researchers argue that the methane and carbon dioxide signatures could also be produced in a gas-rich mini-Neptune with no habitable surface if the atmospheric metallicity is sufficiently high, around 100 times solar. In this mini-Neptune model, methane is produced thermochemically in the deep atmosphere and mixed upward, highlighting the ongoing degeneracy in our atmospheric models where different physical realities can produce similar spectral outcomes. The most controversial and exciting aspect of the K2-18b data is the potential detection of dimethyl sulfide. On Earth, there is no known natural, abiotic process that produces dimethyl sulfide in significant quantities. It is produced exclusively by life, specifically by marine phytoplankton and certain bacteria. Consequently, the reported 3 sigma detection of dimethyl sulfide in the 2023 and 2025 datasets sent shockwaves through the scientific community. A 3 sigma confidence level suggests a 99.7% probability that the signal is real and not a result of random chance, which is often considered a tentative detection rather than a definitive discovery. Professor Nika Midhusudhan stated that this detection, if confirmed, would represent the strongest evidence to date of possible biological activity on an exoplanet, suggesting a Hycean world with an ocean that is teeming with life. However, the concentrations of dimethyl sulfide and dimethyl disulfide estimated on K2-18b are thousands of times stronger than those found on Earth, over 10 parts per million, a discrepancy that researchers believe could still align with theoretical Hycean models. Critics and secondary analyses have challenged the robustness of the dimethyl sulfide signal, pointing to technical hurdles in the data processing. Renyu Hu and his team at NASA's Jet Propulsion Laboratory argue that the signal-to-noise ratio in the mid-infrared instrument data is plagued by unresolved instrumental systematics, where different wavelength binning schemes can yield a potpourri of different planet spectra and interpretations. Their reanalysis suggests that the dimethyl sulfide feature may be interchangeable with other molecules like ethylene or could simply be red noise artifacts. Furthermore, even if dimethyl sulfide is present, its status as a reliable biosignature is questioned. Photochemistry on a sub-Neptune could potentially create organosulfur molecules abiotically. Laboratory experiments have shown that electrical discharges in a mixture of hydrogen sulfide and methane can lead to the abiotic formation of dimethyl sulfide, and the gas has even been detected in cometary environments far from life. To resolve this enigma, researchers are calling for more extensive observation time, estimated at an additional 16 to 24 hours, to reach the 5 sigma gold standard of statistical significance. Even if K2-18b possesses a liquid ocean and the correct atmospheric chemistry to support life, it faces a significant geophysical hurdle regarding the nature of its deep seabed. On Earth, the ocean is in direct contact with a rocky, silicate mantle, a configuration that allows for hydrothermal activity and the recycling of essential minerals like phosphorus and iron. This rock-water interaction is widely believed to be a necessary prerequisite for the origin of life, as it provides the chemical energy and nutrient supply that fuels simple metabolic pathways. However, in a planet as massive as K2-18b, the combined weight of the global ocean and the overlying hydrogen atmosphere creates immense pressure at the base of the water layer, potentially reaching millions of times Earth's atmospheric pressure. Theoretical models suggest that this pressure is high enough to freeze water into a solid state even at high temperatures, forming a layer of high-pressure ice such as Ice 7, Ice 10, or the superionic Ice 19. This massive ice mantle would sit between the liquid ocean and the rocky core, acting as a formidable physical barrier that prevents any direct nutrient exchange between the two layers. Without the delivery of heavy elements from the core, the Hycean Ocean might be a biological desert, incapable of sustaining anything beyond the simplest microbial life. This core ocean decoupling is a primary reason why some planetary scientists remain skeptical of the Hycean world's long-term habitability compared to Earth-like rocky planets. However, new research into the properties of high-pressure ice suggests the barrier might not be as impenetrable as once thought. Studies of plastic Ice 7 have shown that electrolytes and salts can be incorporated into the ice structure and transported through convection over geological timescales. If the high-pressure ice mantle is permeable to these electrolytes, it could essentially create a conveyor belt of chemistry, maintaining a habitable environment even in the presence of an icy barrier, and keeping the dream of a thriving Hycean biosphere alive. Despite the widespread popularity of the Hycean model, a compelling competing theory suggests that K2-18b might actually be a magma ocean world. In this scenario, The planet's internal heat, or its intense greenhouse effect, is so extreme that its surface is composed of molten rock rather than liquid water, making it a hellish lava world wrapped in a deep hydrogen envelope. A magma ocean could also explain the observed depletion of ammonia, as the nitrogen species can be highly soluble in molten silicate magma under the reducing conditions of a thick hydrogen envelope. This model categories K2-18b as an environment as inhospitable as it gets, yet one that can fit many of the observed spectral traits detected by the James Webb Space Telescope. The fundamental challenge for modern astronomers is that both the water ocean and magma ocean models can be made to fit the observed mass, radius, and much of the spectral data. To distinguish between these two drastically different realities, researchers are looking for trace gases like ethylene or specific sulfur compounds that would only be stable in one of the two environments. Christopher Glane of the Southwest Research Institute has argued that observations of similar sub-Neptunes, like TOI-270d, show atmospheric chemistry that is more easily explained by the magma ocean hypothesis, where methane and carbon dioxide are cooked in the presence of hot hydrogen and molten rock. Furthermore, some climate models suggest that many mini-Neptunes in the habitable zone would suffer from a runaway greenhouse effect, where the hydrogen atmosphere traps so much heat that surface water becomes supercritical, a state where distinct liquid and gas phases no longer exist. The resolution of this paradox will define whether K2-18b is a cradle for extraterrestrial life or a sterile world of molten stone shrouded in a thick, suffocating gas. If life does indeed exist on K2-18b, it must operate under a significantly different energetic regime than life on Earth. A hydrogen-rich atmosphere provides a wealth of reducing power which, when combined with oxidized species like carbon dioxide, can release significant metabolic energy through the process of methanogenesis, carbon dioxide and hydrogen reacting to form methane and water. This is an ancient microbial metabolism used by some of Earth's earliest organisms, and on a Hycean world, this chemical gradient could support a robust microbial biosphere. More than 75 kilojoules per mole of carbon can be released from carbon dioxide hydrogenation under Hycean conditions, which is well above the minimum energy threshold required to support methanogenic life on Earth. A detailed comparison of the biological factors between terrestrial oceans and a hypothetical Hycean ocean on K2-18b reveals these differences in stark detail. While Earth's atmosphere is oxidizing and dominated by nitrogen and oxygen, the Hycean environment is deeply reducing, consisting of hydrogen and helium gas. This shift in chemistry dictates that while Earth relies heavily on solar energy and photosynthesis as its primary energy source, life in a Hycean ocean would likely depend on chemical gradients and methanogenesis to fuel its metabolic processes. Furthermore, the source of essential nutrients would differ significantly, moving from Earth's reliance on direct crustal contact and hydrothermal vents to a system that may be dependent on atmospheric rain and external delivery if the icy barrier prevents contact with the rocky core. Studies of hypothetical Hycean biology suggest that warmer surface temperatures would lead to higher entropy and potentially more complex metabolic pathways, while cooler temperatures might delay the emergence of life by billions of years. Since the K2-18 system is estimated to be only about 2.4 billion years old, significantly younger than our solar system, any life on K2-18b might still be in its earliest infancy, consisting of simple, unicellular organisms. This raises the fascinating prospect that we are observing a world in the very process of becoming inhabited, where the synthesis of amino acids like glycine and alanine could actually be energy-releasing or free. The K2-18b saga is merely a precursor to a new decade of extreme exploration. While the James Webb Space Telescope has provided us with the first tantalizing clues, it was not specifically designed to be a dedicated life detection machine. Its instruments, while incredibly powerful, operate at the very limit of their sensitivity when searching for trace biosignatures like dimethyl sulfide in the atmosphere of a distant sub-Neptune. To move from tentative detections to a definitive, world-changing discovery, the astronomical community is already planning for the next generation of observatories, including the Habitable Worlds Observatory and the Ariel mission. The Habitable Worlds Observatory is envisioned as a super Hubble that will be the first telescope designed specifically to search for and characterize at least 25 potentially Earth-like worlds. Using a state-of-the-art coronagraph to block out a star's light, Habitable Worlds Observatory will be able to directly image the surfaces of rocky exoplanets and search for unambiguous biosignatures like oxygen and methane with unprecedented clarity. Meanwhile, the European Space Agency's Ariel mission, planned for launch in 2029, will conduct a large-scale chemical census of over 1,000 exoplanets, including gas giants, Neptunes, and super-Earths. Ariel will focus on understanding the link between a planet's atmosphere and its host star, helping to break the degeneracies that currently plague our interpretation of K2-18b. Over its primary mission, Ariel will obtain eclipses and transits at varying levels of quality to answer fundamental questions about the nature and origins of planetary systems. As our telescopes become more precise and our models more sophisticated, we will likely find that K2-18b is just the first of many Hycean world candidates. Projects like the Pandora mission and CubeSats like SBERCS will continue to monitor the high-energy output of red dwarf stars, providing the stellar context necessary to separate true planetary signals from stellar noise. Decades from now, we may look back at this current moment as the tipping point where the living universe finally came within reach, proving that the recipe for habitability is far more diverse than we ever imagined. We are currently standing on the precipice of a scientific revolution, peering through the lens of the James Webb Space Telescope at a distant world that might finally answer the ancient and haunting question, are we alone? Carl Sagan once remarked that the universe is a pretty big place, and if it is just us, it seems like an awful waste of space. K2-18b represents our best chance yet to prove that space is not, in fact, wasted, and that life can thrive in environments that are fundamentally different from our own. Brian Cox reminds us that we are the cosmos made conscious, and our true significance lies in our ability to understand, explore, and marvel at this beautiful universe, regardless of whether we find life on the first try or the 1,000th. The evidence for K2-18b as a Hycean world is compelling. Methane, carbon dioxide, and an ammonia sink all point toward the existence of a liquid ocean. But the dimethyl sulfide signal remains a mystery that requires 5 sigma proof before it can be accepted as scientific fact. We must be careful not to fool ourselves with pretty stories, as Sagan warned. The high-pressure ice mantle and magma ocean models are sober reminders that nature is often more complex and indifferent than our hopeful theories. The great question remains, if K2-18b is a planet ocean, is it an ocean teeming with life or an ocean of sterile, high-pressure chemistry? The search for life beyond Earth is one of the most profound pursuits of humankind, and as we wait for the next set of data to arrive from the James Webb Space Telescope, we are reminded that context matters and that exploration is in our nature. Whether K2-18b is inhabited or not, its study has already expanded our horizons, proving that the galaxy is full of exotic bridge worlds that defy our expectations and challenge our place in the cosmic order. We continue to wade into the cosmic ocean, one cup of water at a time, searching for the whales that we hope are swimming just beneath the surface of the stars.